So chapter 5 is actually called types of compounds. There are many types of compounds. In fact, you can do in university an entire course for an entire year on just one type of compound, looking at all the subtypes within it. But in this chapter, we're going to look, Julia, at three main ones. We're going to look at acids/bases. They go together like positive and negative. They're the opposites of each other. So by the end of this chapter, if I show you a chemical formula, you should be able to, hopefully, Jasmine, oh, that's an acid, I can tell you why. Or that's a base, I can tell by looking at the formula. We're also going to look at salts. Table salt is actually a subgroup of a larger group of compounds that we all call salts. And then the topic that chemistry majors fear, because it's probably the toughest graduate chemistry course, organic compounds. Which at first were compounds associated with living creatures, but we then learned you didn't have to be living to create them, but it's one of the signs of life. If you're wondering, when we look at other planets, if we're looking for signs of life, one of the things we look for are what are called organic compounds. It doesn't guarantee there's life, but they are compounds that are produced by living things, but there's other ways to get them too. So those are the big three. Let's start with acids and bases. So there are other ways to classify compounds other than just, what's the way we've been doing so far? What was the question that we asked ourselves whenever we saw a new formula? There was two different ways of bonding. What were they? Matt? Okay, so you can classify them in how they bond as ionic or covalent. I guess I wanted the word bonding here for some reason. Another way to classify compounds is by how acid they are, so by acidity. When I say the word acid, what comes to mind? If I'm pouring acid on your skin, what might you feel? Why? How come? What's going on there? We're going to try and answer some of those questions, okay? So, acids. It turns out what acids do, which sounds very benign, very meh, but actually has a huge impact, they release, now, don't write this down, they release, technically, don't write this down, protons, except they're coming from atoms, so we say this, they release H+. Now, what does H stand for? Hydrogen. How many protons does hydrogen have normally? One. That's why it's element number one. How many electrons does hydrogen have normally? One. But if it's H+, what we're saying is it's lost an electron, so what's left? So this is really protons, but because they're actually coming from hydrogen ions, we can say H+, when dissolved in water. An acid won't burn you if it's not liquid, but if it's liquid, if it's dissolved in water, when the acid enters the water, the compound splits up and one of the water gets in between the different molecules, and one of the things that happens is you have a whole bunch of hydrogen positive ions, protons, but since they came from hydrogen, in the water. Big deal. Actually, that explains almost everything. They're part of some foods. Orange juice is acidic. That's why it hurts your eyes if you ever get it into your eyes. Soft drinks are acidic. Lemon juice. What do OJ, lemon juice, soft drinks have in common? They taste sour, and we like that in our food in limitations. If any of you go into becoming a chef, one of the things they'll talk about is, you add some acid to a food, and then you want to add some sweetness. It's part of balancing flavors. So we like soury things, as long as they're not really sour. We have stomach acids help us digest food. Does anybody know the acid that's in your stomach? The name of it? Hydrochloric. What do you think hydro stands for? What element do you think that might be? Hydrogen. What do you think chloric stands for? In fact, the formula would be HCl. Now, hydrogen is a plus, chlorine. You know what? It crisscross balances quite nicely. In fact, it is. Okay. We had a real problem in the 1970s with acid rain, because that tends to dissolve buildings over time. We've gotten better, but now we're regressing again. We got better because the first world North American and European economies cleaned up their pollution, but now we have a bunch of poorer countries that are starting to industrialize, and they're saying quite rightly, hey, you guys got to pollute the earth to develop your economy. Why can't we pollute the earth to develop our economy? And we haven't found a workaround to that yet. So China, some of the African, some of the South American countries, well, they're now starting to create acid rain and things. Some positives: acids are able to remove rust and purify metals due to their blank. Now, the word you guys all said when acid went on you is burning. That's not the fancy science word. There's a fancy science word for burning. It begins with the letter C. Very nice. Due to their corrosive properties. And for some reason, the line divided in two there, but that's one word. Okay. Now, I still haven't really told you what an acid is. I've just told you a bit about some of them and what they do, but that's okay. The opposite of acids are bases. Okay? You can tell something is a base is basic because it feels slippery. Bleach is a base. Oven cleaner is a very basic base, a very strong base. What else? Hint, it's slippery and use it in the shower. Soap is a base. Some foods are basic. Eggs, that's why when you're cracking an egg, the egg white's very slippery. Baking soda is a powder, but when you mix it with water or some other liquid, it becomes basic. Some drugs are basic. So, I wrote here, video, the strengths and weaknesses of acids and bases. Put your pencils down. This is pH scale. Psst, work on the homework later. Okay. pH scale. pH scale is used to measure the acidity slash, now the word that's the opposite for acid when we're talking about measuring, it's called alkaline. So it's the alkalinity of a substance. Alkalinity is how basic something is. And if you want to know how to spell alkalinity, it's on the next line there. Alkanity? Wow. That's a calamity for alkanity. Good gosh. Alkalinity. I mean, the positive of giving you a candy when I make a mistake is that it keeps you guys paying attention, but I can just see an overweight class by the end of the year if I keep going at this rate. So here's a chart. What's in the very, very middle where it says neutral? Water. Okay, I told you that's how we're going to define things here, pure water. So, except it has a pH not of 0, of 7. Anything this way is more alkaline. Anything this way is more acid. And the further away from water, Tyra, the more acid or basic, more acid or alkaline the object is. Stuff on either end would do damage to your skin. Oven cleaner is also, you don't want, you wear gloves when you use oven cleaner for a reason as well. Okay? So it goes from, well, how far left does it go? What does the chart say? 0 to 14. That isn't quite accurate. There are some very, very freakishly acidic things that have a pH of less than 0, but it doesn't make much sense mathematically. It's because they didn't know much about acids when they set up the pH scale. So if you have less than 7, that means you're acid. If you have more than 7, that means you're basic or alkaline. What's the word for 7? What does 7 equal? Begins with letter N. Okay, we call that neutral. So you can look at stuff. Eggs, are they acidic or are they basic? What's their pH level? 8. Okay. Soap, what's soap's pH level? 10, and it's basic and slippery. Milk. Now, a lot of people think milk is basic because Mommy says when I have a tummy ache, she gives me some milk to drink. Well, compared to stomach acid, it's to the right of stomach acid, so it is more basic than stomach acid, but it's more acidic than water. Okay? Using the pH scale allows us to express a very wide range of measurements using a small scale. Okay? So we have 0 is most acidic. 14 is least acidic, but what's the opposite of acid? Begins with letter B. So you can also think of it as it's the most basic or the most alkaline. Here's where the pH scale, Lydia, gets a bit weird. A change of 1 on the pH scale actually represents a 10 times, I'll symbolize that with 10x, but that's not an x, that's a time symbol, increase or decrease in acidity. Say what? So, a solution with pH 3 is how many times more acidic than a solution with a pH of 4? 10 times. A solution of pH 2 is how many more acidic than a solution with a pH of 5? How far apart are 2 and 5? 1, 2, 3, 1,000 times. Every bump by 1 is another power of 10. And the reason it's set up this way is there's such a wide range between acids and bases, it allows us, Brooke, to get these on a scale from 0 to 14. Otherwise, we'd have a scale from 0 to several trillion, which doesn't work very well. A solution with a pH of 3 is how many times more acidic than a solution? Sorry? 10,000. So, a classic provincial exam question. How many times more acid are tomatoes than milk? What are tomatoes? pH what? 4. What's milk? pH what? Okay. How many times more acid are grapes than bleach? Okay, grapes are 3. Bleach is 12. How far apart are they? A 1 with 1, 2, 3, 4, 5, 6, 7, 8. 9 zeros, which is 1 billion times more acid. Can you see why we had to go with this scale instead of just going up by ones? Wouldn't work very well. For those of you who are nerds, this is Courtney called a logarithmic scale. Don't need to know that, but I'm a nerd. How many times more alkaline, more basic, is oven cleaner than ammonia? There's ammonia. There's oven cleaner. How far apart are they? So it would be 100 times more alkaline. Why more alkaline? Because the oven cleaner is to the right. Okay, so acid moving left. Do you need to memorize that? Nope. You're going to have you need to memorize that we're going up by power, that each one is worth 10. But you're going to get this particular chart as part of a handout in a second. What you have to be able to do is read it. Note, nerd moment, pH stands for power of, hey, what is a capital? Huh? Ooh, nice. The P is always lowercase, the H is always uppercase, for what it's worth. I won't take marks off if you write it differently, but again, apparently I can't spell the word alkaline, but I can at least get the pH right. Turn the page. Now we're going to go a little CSI on you. Okay? Unfortunately, I don't have a color photocopier, so your copy is black and white. On the provincial, you will get, I think, this chart in color because the government can actually do color photocopies. But it is labeled, and we'll talk about this in a second. What are pH indicators? pH indicators are chemicals that change color depending on the pH of the solution that they're added to. And in fact, we're going to play with some of these in a lab. You get to do some color changing labs. It's quite cool. pH indicators change color. They're chemicals that change color depending on the pH of the solution that it's added to. I stole this from page 224, but you have it in front of you. So there's going to be 6 that we're going to be playing with. There's one called methyl orange, one called methyl red, one called, anybody want to try pronouncing that? Bromothymol blue. Litmus paper, 2 types. There's red litmus paper and blue litmus paper. Anybody want to try pronouncing this one here? Yep. Phenolphthalein, but yep. And then indigo carmine. There are a whole bunch of pH indicators. These are the 6 that we can use because we can afford them, and they're also not horribly toxic or dangerous. Or they're mild, don't want to put in your eyes or anything like that, but we can play with these in high school. So if you ever see CSI where they're trying to identify a compound, a mystery substance, Conlon, one of the ways you do that is you want to figure out its pH, because then you can look up on a pH chart, okay, it could be one of these 3,000 compounds. You would also, there'd be a whole bunch of other characteristics you would try and identify as well. But if you see them adding something to a test tube and shaking it up, and if there's a color change, this is what they're doing.
Don't they also do that for like airports, for like drugs?
All sorts of stuff. All sorts of stuff. Well, who has a hot tub? Okay, this is when you go check the little strips that you put in there. Those are pH indicators. If you've never done that, your folks have, trust me. So, methyl orange changes from red to orange yellow. And I looked these up. You can kind of tell roughly where the change is, right about here, which is 1, 2, 3, 4. But actually, it changes at pH 3.1, if you really want to be exact. And then it changes to orange-yellow at about a pH of 4.4. In between those two, it's kind of some red, some orange-yellow, because some of the chemicals have reacted and some haven't yet. So methyl orange, they call it orange because it's a combination of red and yellow, and it's a little bit different. Methyl red goes from red to yellow, and in between it's a little, well, here's what I wrote. It's red let's see, right about there. It's red when the pH is less than 4.4. I had to Google these. It's yellow in a pH of over, well, if you want the fuss, 6.2. What's the color that's between red and yellow? It turns out this one is kind of orangey in between those two colors. Bromothymol blue is either yellow or blue. Turns out it's yellow in a pH of less than 6.0. It's blue in a pH of bigger than 7.6. In between those two, you might get kind of a little bit of both. But if you get it all blue or all yellow, you know, oh, I'm definitely less than 6. Litmus paper actually changes right at a neutral solution. What's a neutral solution? What's a pH of neutral? Not 0, sadly. What was it? 7. Phenolphthalein is colorless. It's not just transparent, it's colorless like glass, like window glass, because I guess glass can have color too. So colorless. In a pH of, well, right about there, well, it turns out it's 8.2. Less than 8.2. It's colorless, looks like water. Don't drink it. Turns completely pink in a pH of bigger than 10. Starts to turn pink in between. Indigo carmine is blue in a pH less than, well, way over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and a bit. I looked it up. pH less than 11.4, it's blue. It's bright yellow and a pH bigger than 13. So the CSI part of this, Allison, is as follows then. Let's suppose you have a solution, a mystery solution, and you know it's methyl orange, and we're dropping it into a solution that's a pH of 3.0. What color will methyl orange be? Well, at 3.0, according to here, still red, because at 3.1 is the magic number. Write this down, right? And at 5, definitely orange-yellow, because I said the transformation point was at 4.4. Between those two, kind of some red, some orange, some yellowish-ish. I would probably not use methyl orange to figure out, Brooke, a pH in the 3 to 4 range. It's too close to its color change transformation. I'd go with something else. For example, describe, I wrote here, how the color change of a sample changes as the pH increases from 6 to 11. So using phenolphthalein, pH of 1, 2, 3, 4, 5, 6, it goes from colorless to what color? Pink. Are you guys all on the next page now? Is that right? Well, before I do that, hey, Mr. Dueck, it sure would be handy to have these lined up on a nice single page with a nice, you know what? Here is your reference sheet for this chapter. If a sample turns blue when tested with bromothymol blue, on your chart right now, find bromothymol blue. Put your finger where it changes blue. Just hold it there for a second. What pH ranges could it be part of for that first part? I've scrolled down so I can't see my chart. If something turns blue, Yeah.
Around like 7.5 to 8 is what it turns blue.
But it could be more than that or less than that.
More than that.
Okay, so for that line there, I know above what?
7.5 to 8.
Okay, so I'm going to say above 7.5, check. And it stays colorless when treated with phenolphthalein. Okay, so if it's colorless, what can you tell me for phenolphthalein, which is a word I have a tough time saying without spitting. So Cam, it's going to be a long unit. She sells phenolphthalein by the seashore. So find phenolphthalein on your chart. If it's colorless, what can we be between?
8.3.
Above or below? I need directions here. Oh, below about what?
8.2.
Now that's from the numbers that I gave you in the notes. From the chart, it's below about what? Rough guess. Doesn't say 8.2 or 8.3, does it?
No.
You guys understand where we're looking on the chart? Yeah. So below about, you said 8.3? Okay, so if I'm in CSI and you now had to make a guess, I'm trying to identify a mystery substance, what do we think the pH range of this substance is? From about 7.5 to 8.3. We've narrowed it down using 2 tests. We know it's less than a certain amount, bigger than a certain amount, so Rachel, it allows us to kind of narrow it in. In a real lab with fancy equipment, Jaden, you could be even more specific. Okay. So we just hit 1 o'clock. I think what I'm going to do is I'm going to pause here, and I'll start off on Friday. So Wednesday is your test. Friday is a late start Friday, so the classes are a bit shorter. I'll start off, we'll watch the little video on litmus tests from SciShow experiments, and we'll quickly answer the reading check. All the reading check is it's giving you questions about these pH indicators and powers of 10 and all that stuff. So pause here. What can you work on right now? How many of you finished the study guide? Only a couple, so you can work on that. You can work on the crossword. Any other missing assignments? Let me hit pause.